Good afternoon, and welcome to this Forum 360 session on the digital system model, and a little precocious title about a new frontier in aerospace defense acquisition. This is premised on a vision that's been building in the Department of Defense the last several years, pulling together lots of things associated with the generation and transmission and reuse and knowledge management of using digital systems to describe defense systems and acquisition. And so what you're going to hear today are the three people that carry the water for this in the Department of Defense, making this a reality, going from vision to a real reality. I think I can drive this thing. So the panelists we have today, and I'm extremely pleased to have them come spend time with you and explain what we're doing here. And this will be the batting order for the panelists today. First we have Dr. Jeff Holland, who's with the Army Corps of Engineers in Vicksburg, Mississippi, and Director of Research and Development and Chief Scientist for the Corps. Also Director of the Army Research and Development Center, ERDIC. He also has a couple other titles he carries with him. He is the Service Principal for the High Performance Computing Modernization Program, and that's under his purview, and a lot of the physics-based modeling tools come out of that organization. Jeff is also the Service Principal for one of the 17 communities of interest, technical communities of interest on engineering resilient systems, and that's what you're going to hear him talk about today is the capability builder for this vision of a digital system approach to acquisition. And next we have Dr. Dave Walker, who's the Deputy Assistant Secretary of the Air Force for Science, Technology, and Engineering, works in the Office of Air Staff Level for Acquisition, and fundamentally he's the Chief Scientist of the Air Force, and Chief Engineer for the Air Force. And in his job jar, he is responsible for revitalizing engineering across the Air Force. So he has been leading a number of senior Air Force technical leads on rebuilding or building an analytical framework for the engineering function as well as a knowledge management system. So this all plays again into this digital system, digital thread concept. And then Kristen Baldwin is the Principal Deputy Assistant Secretary of Defense for Systems Engineering, and she's the Acting Director of Systems Analysis. So looking at policies and practices and taxonomy and structure for organizing systems engineering information over the entire life cycle. In addition to, at the OSD level, she has responsibility for how model-based engineering plays in the concept of acquisition and sustainment. So those are not only their job titles and kind of things they're responsible, these are the three people in the Department of Defense that literally have this vision in their job jar. It's their job to execute. So I'm really pleased that they were able to come spend time with us and explain their thoughts and part of this vision, how it all ties together across the multiple elements of the Department of Defense, and it should be a real game changer on how we're going to look at acquisition and sustainment of defense systems in the future. This is the charter or the challenge I sent out to our panel members when we started organizing this thing, and basically bringing policy practices and technology to look at using advanced physics-based modeling, statistical engineering, resilient design practices, look at digital circuit representations, digital manufacturing, digital twin. These concepts we'll talk about as we go along. Simple-minded objective: can we reduce the total cost and cycle time for development and sustainment, total ownership cost for acquisition and sustainment of weapon systems? And I think you'll see it clearly in the presentations you'll see from this group as we go forward. This is really pulling together a lot of the recent advances in high-performance computing and other tools that enable this. I chose to do this to kind of pull together, they each are bringing different pieces of this vision to the table, but they also have a common essence. And Dr. Holland will be talking about engineering resilient systems, which is a 6.1 to 6.3 technology program. So he is building the tools that will enable this. The collaborative environment, focusing on model-based engineering and practices. So you see the essence of engineering resilient systems is an integrated, trusted, computational environment supporting all phases of acquisition and operational analysis. And then Dr. Walker will talk about the digital thread, digital twin the Air Force is putting together in his revitalization of systems or engineering in the Air Force. Two of his priorities are, one is to build an analytical framework for the engineers, and then a knowledge management system to use that engineering framework. And so you see the elements of the digital thread, digital twin. And then Kristen is at the OSD level in systems engineering, where they set policy and practices, and so they have developed some of the taxonomies and the structure of how we want to bring digital information in support of the systems engineering process over the life cycle. So you see these nice dovetailing of these different missions that each of the panelists will be bringing to the table. But it's a unified vision, and pulling all these pieces together, we believe is going to have a very profound impact on future cycle time and total ownership costs for defense systems. Kind of putting in a nutshell, what we're attempting to do is, if you look at all the disparate organizations that exist across a major acquisition and sustainment program in the Department of Defense, going all the way from the research labs to developmental planners to designers and manufacturers in industry. You have testers, you have sustainment people, operators and trainers. All these disparate communities don't communicate with each other. And part of the thrust here is to create this digital thread, a digital system model that can weave all the way through all those disparate communities in a way that you can share knowledge not only downstream as you progress through a program, but to grab that knowledge and bring it back upstream for the next program. So that's the context of what we're talking about in terms of a digital system approach to acquisition and sustainment. And with that, I'm going to, and just a refinement to the bottom of that is, all this is undergirded by the fact that you have to preserve this digital knowledge across the entire life cycle, the 30, 40-year lifespan of a system, and then also be able to share that knowledge across to the next program. And so we don't replicate a lot of stuff and keep doing the same thing over and over again. We create and generate and transmit and share this knowledge. So those are the elements of what we'll be talking about today. With that, I'm going to turn it over to Dr. Holland, and he'll give you a heads up on the engineering resilient systems.
Thank you, Ed. I'm going to stand, if that's all right with you, because either I have to stand or you have to. So you've had lunch and you probably are, just try to stay awake. Fall asleep now would be my suggestion to you, because you want to hear the next two. Okay. Before I start, let me introduce your moderator to you, who didn't really tell you who he is and what he does. Dr. Ed Kraft is from the Arnold Engineering Center, Tullahoma, Tennessee, from the Air Force. He is one of the leads, if not one of the prime leads, in the Air Force in testing and evaluation. He has been a thought leader both in the digital thread construct that you're going to hear about, and also in engineered resilient systems. And to Ed, thank you for convening our opportunity today. Now, I'm from Vicksburg, Mississippi. I'm talking as fast as I can right now. If you can't hear Southern, you will have to ask someone to interpret for you as we go along. Okay. I'm the lead of one of the Department of Defense's 17 communities of interest in science and technology, engineered resilient systems. I will call that ERS from here on, along with these other assignments that I have during the day. The basic idea of engineered resilient systems is this. What we would like is, in an uncertain world, to be able to do a variety of different things. We would like to be able to buy down risk all along the entire continuum of acquisition. From the beginning, from the requirements generation or even previous to the requirements generation process, all the way through the operations and maintenance construct, and then ultimately to the point where a system is retired. Now, to do this is a pretty challenging construct, because we live in a world where we have rather rapid changes occurring all the time. Certainly within the construct of an individual acquisition cycle, we have at least 5 different technological changes that occur just based on computational capability alone. On top of this, you have major changes in threat. You have the major changes in the battle space environment that you're operating in. You have major changes in technology and science on into itself, and how all of this is integrated together in some fashion or form. What that seems to require is an effort to be Nostradamus, to be able to project into the future what it is that's going on. And rather than suggesting that that's possible, let me just propose to you that the idea of being able to use solid ground truth constructs, such as those we can get from a combination of modeling and simulation and focused experimentation, coupled with trade space analysis, coupled with a very effective and efficient representation of the actual environment that we wish to operate in, and finally, coupling all of that with the mission context we wish to operate in, will allow us to gain a great deal of insight into what's likely to happen with a particular acquisition strategy. The basic idea that we're talking about here is one that involves changing our paradigm from, in a design perspective, from one of being a point-based construct where we basically say, here's a ship hull, and everything that we want that ship to do must fit into that. Or here is an airplane fuselage, and everything else has to be hooked to that in some way. And in the case of the ship, that is perhaps the worst case scenario, simply because what actually has happened traditionally is from seakeeping analysis, we come up with that initial design of the hull, and then we literally pile everything else in until we decide that the radar cross-section or the seakeeping capabilities are such that we simply can't operate that way. Okay. So how can we keep from doing that? And the answer is by having a data-driven process that in a design sense would be referred to as a set-based design construct instead of a point-based design construct. Simply put, how do we carry information further through the system and allow good decision-making to pare down the areas of greatest efficiency or greatest interest in our very large domain, our n-dimensional space that we would have for alternatives? And simultaneously, how do we move heavier engineering and science to the left in the acquisition process so that we feel that we have common or good ground truth to use to make decisions? I mentioned the basic components of this idea of ERS, and they are shown here. Advanced modeling and simulation. And I'm going to really concentrate on modeling today, and I want to differentiate for a second modeling from simulation. This is not a universally true way of thinking of it, but one that I've come to espouse. The department has a significant portion of modeling simulation capabilities. In this conference, you're going to hear about a lot of different types of capabilities that are both modeling and simulation, but I think you're going to hear people use the term interchangeably, and I don't believe they're interchangeable at all. Modeling to me is something that is basically physics-based. It's something that I have some basis of truth for, and I understand that basis. So I'm going to refer to models as those things that are based on the Navier-Stokes equations for the sake of our discussion today, or Maxwell's equations, somebody's equations, not the Holland equations. There are some of those, and they always seem to turn out negative in the process, okay? Simulation, on the other hand, is how do we manipulate a series of different entities with different attributes and gain insight from that in some fashion that may or may not be physics-based at all. Many years ago, while standing in Fort Leonard Wood, Missouri, which, by the way, is a place you really have to be going to get to. I mean, at least Vicksburg has an interstate going near it. But I was standing there and I was watching a simulation of semi-automatic forces, and I was talking to a Sergeant Major, and I said, "Sergeant Major, what's that line segment you're crossing there?" And he said, "That's a river, sir." I said, "Sergeant Major, how deep is that river?" He said, "It's 40 meters, sir." I said, "How wide is it?" 400 meters, sir. My father had been a chief warrant officer, so I knew he was actually calling me a name by calling me sir. And so I said, "Will that Bradley fighting vehicle actually swim?" He said, "No, sir." I said, "Well, how do you propose to cross this river?" He said, "I click this button and it goes over there." We don't really want to do that. As we see more and more about the possibility of computational capability replacing actual experimentation or augmenting it in some very real fashion, the responsibility falls on those of us who have grown up doing computations to be absolutely certain that we verify and validate the capability that we're proposing. Because in the case of defense systems, we're talking about the lives of people in these processes. Next component of this is the idea of mission context. How do we warfight the capability that we're describing? Either in a portfolio sense, through a combination of capabilities, or through a single capability, such as an individual aircraft. The next is environmental representation. My hypothesis to you is that in a classified environment, I should be able to properly simulate, in this case, or in some cases even model any environment on this planet. Above it, under its seas, underground, or above it. You say, well, we can't really do that today. No, but we're very close to being able to do that today. So rather than running geotypical environments to do our analyses in, we can run real environments to do those analyses in. And finally, the idea both of a trade space. Think of a giant optimization problem, if you would, for a second. And then secondly, the ability to really mine that trade space to fully understand the implications of what we are learning, to actually learn from it, not simply propose ideas to it. I want to give you an example that does not come out of the defense industry of a bad version of this. Among the many things that I do in my day job, we also do civil works related analyses for the country. In fact, when you think of Corps of Engineers, what you normally think is that you have a beautiful river and we take it and make it really straight and really ugly. Okay, now that's not what we do anymore. All right, that's what was done perhaps in the 70s and 60s. All right, but we were doing an analysis after Sandy came through in the Northeast, and we had a specific set of questions that were posed to a very large database that we had of all of the surge potential that could exist in and around the Hoboken, greater New York City area. And we answered all those questions, but you know what? Because we were not mining that database as effectively as we could have, we missed the opportunity to make some important changes potentially on exactly how the systems could have been operated to reduce flooding in those areas. Okay, so what we want are trade space analytics that help us understand things, at times even things that we are not looking for. And then finally, we need an architecture that ties all these together, and that architecture does not exist in the Department of Defense. At least not today. All right, this is an idea of what that architecture would look like. It would not be designed to handle a single capability, a particular platform, but would be designed to handle any of the platforms that we are interested in. And it would be designed specifically to support acquisition, again, all along the lines from requirements generation and the insight that goes into those, into analysis of alternatives, ultimately into the manufacturing process that goes along, finally into operations and maintenance, and then into retirement. These are the technical players that are involved in what we're doing. You may see the names of some of your organizations on here. I did not go to the web and pull every logo that I could find. There were at least 8 more logos on the web that I did not put on this one. So if yours is not on there, please don't be offended. The important part to this story is that these folks actually are doing more than a cup of coffee. There's money changing hands. What a bizarre idea. All of it legally. I want to be sure to say that in case this is in fact being recorded for posterity. Okay. So you've got all of these groups involved. You've got different levels of industry involvement thus far. Those range from technical discussions that have occurred between the science and technology components of those organizations and the department, all the way up to contractual activities that are going on between the department. And in some cases, the use of IRAD to support this on the parts of those organizations. We've got architecture products, and the key part of this architecture is the idea of building an open systems environment. Of course, you will not hear anybody not say they're going to build an open systems environment. That's the buzzword of the century. I'm also an IT geek as well as an engineer, so I know that we're supposed to say that. The point is that we will publish open standards. And if you have a capability that you want to hook to this, you bring your 18-wheeler and back it up to our loading dock. We will describe that loading dock environment to you. What it should do is allow you to use all the other tools that are involved as well, except for those that are proprietary. And the proprietary in this case would be those of industry, where we sign non-disclosure agreements. There are a lot of trade space capabilities in the system. We have already run a problem with the Navy where we looked at 2 billion alternatives to populate a very large database. What will we do with that database? We were able first to help the Navy understand exactly where their sweet spot was for a particular acquisition activity. From that acquisition activity, we keep all of those data. We don't ever throw them away again. Okay? And that's important, and you're going to hear more about that in particular when David talks to you about the idea of digital thread, is that we keep those because they represent an insight that we can mine before we begin the next process. Many of the physics-based capabilities in the department are in the system now, the most important of which are, at least at this time, are the CREATE tools out of the HPC modernization program, and there was a session this morning on CREATE AV. There are CREATE tools for both fixed wing and rotorcraft. They're validated for ships, for antennae systems, for ground vehicles, although that one is behind the rest of the capabilities just because it started later, and also for sensor systems. All of these are highly validated. We have the both good fortune and bad fortune of having had the opportunity to validate many of these, for example, the blast codes, against 15 years of warfare that have been going on for our armed forces. These capabilities, by the way, represent what I will call to you truth for the sake of discussion. In doing a trade space analysis, one can either do it for the standpoint of insight and learning, in which case everything is relative to some baseline, or from the standpoint of understanding whether any of those answers actually has any specific validity associated with it. At some point, that latter version is needed. Knowledge management products, we've got several of those, and I have the good fortune to be the knowledge management lead for the Corps of Engineers. This is a pretty challenging activity because giving you the ability to Google the whole thing is a pretty straightforward process, but turning out the experience that subject matter experts have, codifying that in some sense and getting that out to people who know what they do is a very different story. We've done applications to ships. I mentioned one of those just a second ago, so I'm going to pass by that. You see 3 different examples of what we've done with that. But one of the critical things that we did do early on, working with the folks from the Navy at Carderock, who are also the people who work the CREATE tools for ships, is that we got them to put together 2 design teams. The first design team had a group of people in it that had over 30 years of experience, the people that are unfortunately becoming fewer and fewer in the organizations. They knew exactly how to do things, and they did it the very traditional way that they did it. We then took a group of people who had 2 years experience, gave them all of the ERS tools, and turned them loose in the process of a set-based design construct instead of a point-based design. Gave them both less than 3 months to do their analyses and then looked at the results. We imposed a series of change orders, if you will, all along the way, and even changed what their cost curve requirement was about halfway through the activity. And we found that using the tools and using the set-based construct actually allowed for an equally good, if not better, result in terms of overall risk buy down with an almost analogous cost in this particular case. In fact, if we had taken the 30-year individual who was leading the Naval Architecture Group for the point-based design, the traditional way of doing it, then that group actually would not have been able to complete their effort in the time that was allowed. We've had application to rotorcraft, again, using the ERS tool, the CREATE tools. In this particular activity, Boeing came in with a new design for a proposed blade replacement for one of our helicopters. We were able to do an analysis that showed, and that design, by the way, was done completely through IRAD. We were able to validate that capability and put that out for people to evaluate through test and evaluation in less than a couple of months. the results showed, in fact, that the proposed idea, in fact, would work. The code that was used for that was Helios, and I'm not going to go into any details about that today. We've had a number of different types of activities that were done. One of the presentations that was done just before launch was on the A10 engine inlet. We've done similar types of things for tail rotors for the H60. And you can see that overall what we've had the ability to do, and this was a demonstration that we did with Ed and some of his folks and some of the people at Air Force Research Laboratory, was we combined the idea of concept design with the ability to do these trade space analytics, with the ability to actually evaluate whether or not the thing would fly for the mission context that was required. We created an entire database of those, and that information actually went into the analysis of alternatives for the new proposed cargo plane. This is the roadmap, because you've got to have a roadmap. So there's your roadmap. I'll be asking all of you to sign a waiver stating that you in fact saw it, so that I don't get held accountable for not showing it to people. But so we've got 10 years. How much of that 10 years is actually good? At least 3. And then technology will change enough that we will change up what we're doing, because that's the way it works. But as of today, that's 3 years of real possibility there. And what we wanted to do in FY14 actually got done. But with that, let me stop and turn this over to Dr. Walker. And I'm sure we'll take questions at the
afterwards,
end.
Yeah.
Okay. Thank you. Okay. So Jeff talked about the engineering resilient systems, and that's really what we're trying to do in the Air Force, is leverage what he's doing and turn that into the acquisition process that you use. And we're calling this now owning the technical baseline. That's Dr. LaPlante has laid that on us as one of his priorities. It actually fits very well with where we've been going all along and trying to move toward a better technical understanding of our systems, better ownership from a government side of systems in the future. And the digital thread is a key component of being able to do this. And I'm going to try to go through these and kind of show you how this all fits together. To kind of set the stage, I was running an Air Vehicles Directorate in the Air Force Research Laboratory back in the late 90s. And one of the initiatives we had back in that time was a thing called model-based science and technology, which was linked into what the old Aeronautical Systems Center was doing in model-based acquisition. And the whole concept was to do ERS. Really take advantage of modeling and simulation so that you could do your S&T early, build that digital model and carry it forward as you move then into acquisition, and carry a digital model through and build against the digital model, correct your model as you started building physical models, or physical systems, but have this throughout the life of the system. And you know, the long-term vision was, well, you ought to be able to take this and turn it into a logistics support tool in the future. Now that was in the 90s. That was 99 when I started that. I left there in 2001, and I think that's about where it all dropped and ended. The good news is there's a lot of folks still thinking about this, still working on it, but it never moved beyond that. Now we move forward to 2014. I'm up at the Pentagon now, and I have an opportunity to go back and to try to turn some of those ideas we had back in the 90s into reality. And at the same time, the folks over in AFRL Manufacturing Technology, the Mantech organization, we're looking at digital system models and digital thread and how you can use that from manufacturing perspective and how you carry that into logistics. At the same time, I've got Ed down at Arnold, who's looking at how can I take advantage of digital systems models and ERS that Jeff's working on and pull that to help me do flight tests and ground tests more intelligently. How can I reduce the number of actual physical tests I have to do and verify my models to be able to predict what the performance of the system will be? And then on top of that, I had some folks asking questions back in the pre-milestone A, back in the first concept of systems. How do I really look at a system in a virtual environment and figure out what it is I need to build before I go bend metal and buy something to make sure I'm really buying the right thing? All these things were happening independently, and it all came together under a study that former chief scientist of the Air Force, Mark Mayberry, ran under his Global Horizons, where we, as part of that, one of the things, one of the panels I led was on kind of the supporting technologies that were out there, and this is one of the key supporting technologies we brought together. We said we really need to bring together this idea of digital thread, digital systems modeling. A lot of work's being done, a lot of people are actually using it, but we need to figure out how to bring this and make it a consistent thread, the digital thread, through the entire acquisition life cycle of the system. So this has all fallen in the right places, the right time. And of course, now we have extra help because Mr. Kendall has put out his Better Buying Power 3.0, which Kristen's going to give you a full explanation of when she gets up and talks. But to do this Better Buying Power 3.0, this is all about performance and engineering of the system. And it really depends on having a digital thread and digital system model and a model-based development capability to be able to execute what's in the Better Buying Power 3.0. So everything's falling in place in the right time. And the whole idea is here is how do I use this so I can get better insight, make better decisions? How does the government do independent assessments? Because right now, we're dependent upon our contractor partners to provide us assessments. We'd really like to be able to do internal assessments, particularly early on in a system design process, early on, pre-milestone A, when we're really trying to figure out what is it we actually need. How do we make trades across multiple domains? We don't have that ability right now to rigorously be able to do that. Really want to take advantage of these, the model-based framework to be able to test out ideas and to come up with the best possible system for the future. And the last thing we really want to do is we want to optimize reuse. This is an amazing thing, but if I want to ask somebody about a model, let's take the F-15 as a good example. Air Force has, you would think, we have a fleet of F-15s. We ought to have an F-15 model, probably a different one for the A's, for the C's, and for the E's. But in reality, we probably have 100 different F-15 models that we paid 100 different contractors to design for us, because every time we have a problem that somebody wants to test out something against the F-15 or test something on the F-15, we pay them to go to build a new model to go do it. And that's something we want to break down too. Let's get down to where we have the Air Force approved model that we use. Really take advantage of that. So this digital thread idea is to really try to streamline that entire process and integrate it into the acquisition process. The other thing, as I said, Dr. LaPlante has his acquisition priorities, and one of those is owning the technical baseline. And a key part of owning that technical baseline is having that digital information that you need to be able to make key decisions about your acquisition programs. So you have to have the access to that information. You have to have the ability to actually manipulate that information. So some of the key things that he really talks about here is that you need to have access to the system design. Yeah, you need to we, the government, need to control the interfaces in our systems. We need to have the ability internal in the government to exercise our models and really have an end-to-end understanding of what they're able to do. We are the ones that need to control the data on the system. It doesn't mean we have to own the data. A lot of people say owning the technical baseline means you want to buy all the data. No, we want to have the access to the data and be able to exercise the data. And the same thing on the data rights, it falls along that line. We also want to try to move more toward open architecture so that we can actually use systems that are very open to modifications in the future, both for government going back and doing the modifications or for opening up the competition in systems in the future. And the last thing on this, under the technical baseline, is we really need to understand the technical risk and the issues associated with the program. And it's something that the Air Force has kind of abdicated under the TSPR process. We say we really don't care about technical risk. That's not our problem. All we're going to do is we're going to put a performance-based contract out on the street. And as long as you meet performance, we really don't care how you get there. And that has really led the government to not really understand the risk associated with this program. So we want to return back to where we understand that. Again, to do this, we have a number of tools that are out there. And the digital model is one of those tools that allows us to do this. And we really need to take better advantage of those digital models and really maintain those digital models throughout the life cycle of the system to be able to do this properly. The other thing is, back on the ERS side, is the prototyping. Jeff talked about the virtual prototyping. How do you go through system design and get through virtual prototyping so that before you ever bend metal, you have a pretty good idea of what you need and how it's going to fit into your overall architecture that already exists, existing systems and other future planned systems. This is something that we do in fits and starts in the Air Force, but we really don't have a consistent process in doing it. We want to move to a much more consistent process of doing that virtual portion of the design. But then move beyond that. As you go through your virtual design, you're going to find out there are certain questions that you still need to have answered that you can't do virtually. Or there's technologies that are new that while you can virtually show that they work great, you know, I used to be a flyer. I don't believe it until I actually go out and fly it. So there's times you're going to have to take things out and actually do prototypes, do experimentation, and find out, improve either one, that they really work, or find out how they work and how you can apply them and what new capabilities you can get through new technologies. So we have this other new process that we're putting in place that is called the experimentation and prototyping. And if you really look at this oval, or as Dr. LaPlante likes to call it, is his jelly donut. This is the kind of the entire development process for a system all rolled up into one big circle with everything you could possibly think about in it. But it's really important when you look at this, because this starts with that centerpiece of the science and technology, the experimentation, the prototyping, the virtual work that you do. All these things come together to help you work that decision cycle as to what is it that we need to develop for the future. How do we build systems that cover the domains that the Air Force works, which are the aerospace and cyber domain? How do I determine, what's the system of systems or family of systems I need across all those domains to allow the Air Force to effectively accomplish its mission in the future? So all this rolls in together to give you the ability to bring in new concepts, new ideas, test them out, do prototyping in, both in the virtual domain and in the physical domain, do experimentation, and from there birth future systems or modifications to existing systems. To be able to do this, particularly when you look at the virtual side of it, you've got to have that digital model that's available to you. And when you do those digital models, carry that digital thread through so that I have that, all the information I gain from that I then take into system development, system design, and into flight tests and into the manufacturing. But then I want to take it one step beyond that. And this is where the Mantech folks came in. And that is, I want to go beyond just manufacturing, but also build a digital twin for the as-built system that I can now use for helping me support my logistics side of my air system in the long term. So now that I've talked a lot about this, I'll define what I'm talking about. So digital thread. It's really the digital entity, the digital representation of the system. And it's something that starts from the first time you start thinking about what it is you want up until the day that you retire the system. It's all that digital data, the digital system model that goes along with it. Digital twin is an actual digital representation of an as-built system. And a digital twin, you can do it in two ways. One is you can have a digital twin which represents all the systems, which is one approach to it. The approach which I really push and I think is a much better way is a digital twin which is as built of a single system. So every tail number aircraft would have its own digital twin that I would then use to help support the sustainment of it. But these are when you hear digital thread, digital twin, a lot of times they're used interchangeably. They're not quite interchangeable. That digital twin really is an as-built piece of the digital thread. So what are we doing with this? So a lot of work has been done in this area for several years now. And when I got into this job, Ed called me up with what he's doing with the Create AV out at Arnold and looking at how they can take this to try to improve flight test. The Mantech folks had me over for a PMR to look at what they were doing, and they brought out the digital thread, digital twin concept. And then I had over in my CMAF facility in the Air Force out at Wright-Patt, they were working the ISR multi-resolution analysis capability, which is really looking at a pre-milestone, how do we do a good understanding of the entire ISR architecture and how new systems would fit into that architecture. When you look across this, these are all attacking a problem using a very similar digital thread approach to them, but they're all disjoint. So what we try to do is bring these together into a single set of pilots that are really aimed at trying to define what the Air Force needs to do to really adopt this digital system model, digital thread approach. So the first one here in this pre-milestone A. This is really the one that feeds back into that prototyping and the virtual prototyping side of the world, is how do we develop an architecture and a framework within our simulation environment, and the SIMAF is the Air Force's simulation environment that we are using right now, where I can actually test out new ideas. This is both constructive simulation, but also I can do some pilot in the loop simulation. I can also do some simulation involved in live operations. And so what we're trying to do is get the full live virtual constructive capability built into the SIMAF capability so we can actually try out new ideas and fly them before we ever go build anything. So the first step in that was you got to build that framework, you got to build that architecture to operate in, and that's what this ISR MRA is. So that's become our pilot to start off with on the pre-milestone A side of it. The second pilot that I've got running right now is this one with Create AV. And this one, Ed is leading up, really looking at, I have a system that I've already developed. I have digital system models already developed with that system. Can I go back and learn from that how I could have predicted outcomes of wind tunnel testing before I ever did the wind tunnel testing? The good thing is I've got a complete database of the wind tunnel testing, so I know what the reality is, and I've also got the complete digital system model. Now it's just comparing the two to try to learn how can I reduce the amount of wind tunnel I do, how can I just use it as verification of my system model and improve my system model versus going out and testing every point in the envelope in the wind tunnel and then carry that into flight test, redo every point in the envelope again in flight test. How can I really leverage this digital system model to reduce the time and cost of testing? And then the last one is looking at now at the manufacturing side. And the first one we decided to go test out there was the material review board process. So when you have a non-conforming part coming off the line, it goes to a material review board. The material review board looks at it and determines whether or not it meets requirements despite the fact that it's non-conforming. If it gets passed by the material review board, it just goes into the system as a part, or it goes into an aircraft as the part of the aircraft, and it's no longer tagged and carried. And what we want to do here is anytime you have a non-conforming part that goes through this process, we want to tag it and build the digital twin of that part and carry that for the life of that part so that you understand how that non-conforming part really impacts your system in the long run, instead of just having it become a now approved as a conforming part even though it's non-conforming. And so that's the idea there now, is that simple digital twin of those simple parts. That's the first step. We really want to move to a digital twin of the entire aircraft. But we wanted to go off first with this pilot project just to show that you can do it there and be able to track it, be able to build what is the data information that you need to have, the data package you need to have to go along with that allow you just to support a single part that is non-conforming. So these three pilots are ongoing. Now, while I have these ongoing as kind of the pilots that have been put in place by the real advocates of this, I've also got under the Owning the Technical Baseline 4 different acquisition programs that are really piloting the acquisition, Owning the Technical Baseline, and will now be picking up information out of these and trying to move them into the acquisition process. So the first one is in the JSTARS recap. We're on a process now to figure out how we're going to replace our JSTARS aircraft here in the future. So since it's a new program, it's right in time to be able to apply these ideas. How do we start working a digital thread with that system as they go into the milestone B, carry it through the manufacturing, and hopefully as we move forward, we'll actually build a digital twin of each one of those aircraft as they come off the line, and that'll be our first real test of this. We have another one in the TX, our new trainer replacement for the T-38. Different kind of program because it's most likely going to be a COTS program. So now I have a question, how do I manage the digital baseline, a digital thread of a COTS system? So that's a different flavor that we want to look at. I've got a ground system out at Space Command at SMC in LA, the ground system for the Global Positioning System, the OCX, that they're looking at how they use a digital thread to help them manage that system through its lifetime. And then finally, I have a cruise missile, the long-range standoff down at Eglin, where they're looking at the digital thread as well. They're a missile that has really trying to take a different approach to design of the missile, and in doing that, they really need to have a good understanding of the manufacturability of the missile up front, and in doing that, they're starting to have to understand what is the information the government really needs to have to be able to do that, which means they need to have good digital system models up front, including the manufacturing models up front, so they can ensure they can build the missile with the reliability required as they go into their production decision at milestone C. So the four major systems that we've got forward that are going to take these, what we're learning from these pilots that we have going, and turn them into actual acquisition systems. So we're really moving forward at this at a pretty quick pace within the Air Force. So this is important. To be able to do what Dr. LaPlante has asked us to do in the owning the technical baseline, to be able to do what Mr. Kendall is asking us to do in the Better Buying Power 3.0, we really need to have this digital thread and really understand the digital system models and be able to exercise it within the government. This also is not only going to help us in our acquisition program, but in that digital twin side of it, should actually give us a better capability of sustaining and reduce the cost of sustaining long-term of our systems. The pilots are underway. We're already starting to see some impacts. The ISR MRA has actually been very successful and is helping us reinvigorate our CMAF process and the use of CMAF. And this is becoming a part of our strategic roadmap as we move into the future. And the last piece of this is that we're off running with this at the same time that OSD came down and said, we really need to exercise our digital system models much better than we have been in the past. And so when Ms. Baldwin came to us and said, we need to do this, we came up and said, yes, we agree, and here's how we're doing it. So we're really teaming up well between what OSD is doing and with their digital system model, what we're doing with our digital thread, and really leveraging the engineered resilient systems to be able to do this. The work that Jeff's doing has really helped us move forward into turning this into a reality. And so with that, I'll turn it over to you.
Thank you. That's a great lead-in, because I was going to start my talk by saying, this may surprise you, but it is not always the case that the OSD part of the Department of Defense and the services are on the same sheet of music and collaborating and moving out in a common direction. Yet that is the case for this particular initiative that we are jointly converging on. So what I'd like to do is sort of end our talks, the talking part of this panel exercise, by pulling all this together and describing what we're doing at an OSD level. But I think before I start to do that, it's useful to reflect on what are the drivers for change. We heard a little bit in the very opening plenary session this morning that there's opportunities and that there's a need to perhaps think about engineering for the next 20 years. And so what is really driving that? We're reflecting a lot on that in how we seek to shape Department of Defense systems engineering for the future. And it's really driven by the realities of what our Defense Department needs to be able to do, and the capabilities that we need to be able to achieve and sustain. Our strategic guidance is asking for a military, a defense department that has the capability to be flexible, agile, ready at any time for adversaries that are known today and for the unknown adversaries in the future, not only just adversaries, but for operations and humanitarian assistance and all the multiple numerous types of missions that our troops are out there performing for us, and that our Defense Department is performing for the nation, anywhere, anytime. And the strategic guidance also very specifically points to the technology advances, the capabilities that we have to be able to take advantage of and deliver as part of this overall system. How does that strategic planning guidance and those realities drive the complexity of the systems that we are trying to acquire today? Well, there's a couple key challenges that we face in acquiring defense systems that drive this complexity. We know that we have a dynamic set of threats and different dynamic missions that we must be able to achieve and accomplish. We have to assure that our systems can complete their current mission performance, while also being able to support future unknown environments and requirements that are changing. The op tempo of the theater where we're placing these systems, where we're operating these systems, is very, very rapid, and we cannot always predict where our missions are going, what we're going to be faced with in the future. We also have a diverse set of stakeholders that our systems are engaged with. Dr. Walker talked about system of systems and families of systems. So did Dr. Holland. And so we know that to achieve a mission effect, it takes an integration of multiple systems. And when you think about those systems and what those individual system requirements are, their individual requirements may have nothing to do with that joint mission effect, yet they have to be able to come together, and we need to be able to engineer them to create that effect. We also need to be able to create and engineer our systems for this resiliency, to be able to be resilient to threat, to be able to be resilient to environmental changes, operational changes, considering modularity to enable competition in the future, and really to fundamentally enable innovation, creativity, like we heard about this morning at the opening plenary, as well as sustainment, which Dr. Walker also talked about. And bottom line, we're also under severe fiscal realities. Our budget is resizing right now, and yet at the same time, the demand for the Defense Department, the demand on our services, on our troops, is not declining. And so we need to be able to design defense systems that are affordable and are designed with cost in mind and can be sustained over time. So now, what does all that mean for the systems engineer in the Department of Defense? Systems engineers have to be able to execute a certain set of critical attributes. Our engineers, and we are, by the way, I think we are one of the world's largest engineering organizations. When you total up the military and civilian engineering workforce in the Department of Defense, it's over 100,000 engineers. And as a single entity, that's really probably the world's largest entity of engineering. And so these engineers are driven in several really complex and critical ways. We need to field and maintain a capable workforce that knows and understands how to create flexible designs that can adapt to these known and unknown missions and threats. They need to be able to design and factor in cost and affordability as a critical requirement in the trade space. They need to be thoughtful not only about designing their own system that they're responsible for, but for how that system is going to integrate with other systems across a family of systems and be sustainable and actually integrate with an environment and an enterprise as well. We, as systems engineers, we are very rigorous with our process, but we also, at the same time, know that we must balance that rigorous process with being agile and maybe taking advantage of some new tools and techniques and delivering perhaps partial capabilities over time. And so our engineers are really stressed to be able to achieve that balance. And finally, we must be able to safeguard our information, and we must be able to apply these systems. We need to be able to understand multiple diverse domains and functions of engineering. Our engineers are designing business and management systems, they're designing command and control systems, they're designing aircrafts, land, sea systems, the broadest spectrum. And so what all that comes to in terms of modeling is we really have an opportunity here to take advantage of the tools and the technologies to enable these engineers to be able to achieve and deliver and design these complex systems. And so what we're trying to do at the OSD level is to really initiate this change and transform the state of systems engineering practice. And this is one aspect of how we believe that we can do that. Because the models, better use of modeling and the technologies that we've been talking to you about today on this panel enable our systems engineers to have a better ability to maintain consistency about the system that they're designing, to integrate these technical as well as non-technical aspects, and really understand all the perspectives under design and development and throughout the life cycle. So that's what's driving us. And then, and so the way that we're trying to achieve this change or transform the state of practice first starts with our policy, of course. And so one of the things that you'll see in the emerging, the new update to the DoD 5000 acquisition policy is a very specific emphasis on modeling inside of the acquisition process. So program managers is policy that models, data, and artifacts will be developed, integrated, managed, and controlled throughout the life cycle to be able to help these decisions to be made, to be able to have understanding of the system and the risk and the drivers of cost about those systems, and how we are able to meet, whether or not we're able to meet performance specifications for the systems. At the same time, Mr. Kendall is about to unleash and implement a version 3 of Better Buying Power. This was started by Dr. Carter several years ago with Better Buying Power version 1, which really focused on cost consciousness and affordability. Better Buying Power 2.0 had a real focus on the workforce and making the right decisions and making smart choices. Better Buying Power 3.0 really falls squarely within our engineering and technical lane. And it really is an opportunity for all of us as a large community to make a difference in the way that we are designing and delivering these systems. It is, Mr. Kendall's focus here is to make sure that we can continue as a nation to achieve dominant capabilities through technology superiority as well as and enabling innovation. So that is the focus. And I know this is a bit of an eye chart, but I'm going to talk about just I'll mention a couple key initiatives where we believe that this notion of digital and modeling capability and advancing the engineering competency and advancing engineering state of practice can help to achieve some of these critical Better Buying Power 3.0 initiatives. The first is, I'll just have 2 slides here on our long-range research, development, and planning initiative. Secretary Hagel in November came out with a description, a memorandum detailing the Defense Innovation Initiative, which has several different key aspects that it initiated. One of those was a long-range research and development planning program, and what this is a recognition that that we need to enable innovation to occur, and we need to take advantage of some game-changing technologies, if you will, and make sure that as we downsize our budgets and as we decline perhaps in force structure, that we're not declining in our innovation. And so there's a real direct attempt to identify for the long term game-changing technologies that may be able to enable the department to create new and mission-changing capabilities for the long term. So there is a RFI that has been put out on the street. Many of you may have already seen this. It can be found on the website that I provide here. But the RFI seeks, and I believe that responses are due sometime this month. And so we're seeking to identify these high payoff technology opportunities that the department can invest in to really shape our material investments, our future complex systems, or other opportunities to be able to make sure that we maintain that technology superiority that we're very concerned about over the long term. That we can enable us to better partner with non-traditional defense partners. So we've talked a little bit about partnering with commercial industry. Here at this conference, we're partnering across our agencies that this conference represents, and these broader communities. So the department seeks to increase that partnership. And really focuses on making a change that we can start to see in the next 5 years. A couple other items, aspects of better buying power that really can be enabled by the digital thread, digital modeling concepts, not only from a game-changing technology perspective, but modeling enables us to really, as has been described by my co-panelists, enable us to partner and trade and share information better across the acquisition requirements and even the intelligence communities. If we're able to better share knowledge and information, to model the behaviors and have better understanding of the capabilities, it will help us to build these stronger partnerships. That's one of the key initiatives under Better Buying Power 3.0. We want to also be able to better anticipate and plan for emerging threats. But the key word in that initiative that we believe this benefits is the word responsive, because this is where we have to think about designing our systems so that they can be responsive to these unknowns. Increasing the use of prototyping and experimentation, that's natural, it's already been discussed here. The engagement with industry, providing requirements early on in the acquisition process. Well, how do you do that? How do we describe what our performance requirements are? How can we get away from written description of requirements and imagine a state where where we can provide a model to describe the performance that we want, or a model to describe the concept that we have, and vice versa, that you can also communicate with us much earlier on in the process. Dr. Walker mentioned development planning. This is fundamental to early on trading of these concepts and ideas to mature the art of the possible, and to think about the 10,000 or the 1,000x times of different trades and alternatives that we might be able to consider. We believe that we also might be able to reduce cycle time through this use of these models. I mean, fundamentally, that's one major bottom lines. We need to reduce total ownership cost. Strengthening organic engineering capabilities. Mr. Kendall this is one of the true heartbeats of what he is espousing as he rolls out Better Buying Power 3.0. He recognizes, and you'll see this repeatedly throughout the white paper that he's generated, as well as his implementing guidance that's being drafted right now, is his foundational belief that engineering is central to the delivery of successful systems and the management or acquisition of successful systems. And so he seeks to strengthen our organic engineering capability, not only just the people, but the tools and the models and the capabilities and the engineering environments that exist in order to make our engineers as capable as they need to be. And finally, to improve our leaders' ability to really understand and mitigate the technical risks. So that's a major initiative in 3.0, and we believe that through better understanding and representation of our systems and our designs through these models and through the data that represents them, we will have a better, more rigorous way to explain and articulate and make decisions, make hard decisions on during the acquisition life cycle. Systems, maybe just a little bit of a broad view that we take about the use of systems modeling in the acquisition process. There's an opportunity for the use of models broadly in many aspects of acquisition. We've talked about use of models to enable conceptualization, to enable the design process. They also help us to enable and estimate the resource estimation process. They help us to understand how best to deploy operation and operate our systems and sustain. Benefits are not limited to engineering. We focus a lot, we represent the engineering community here on this panel and largely at this conference. But use of models really is beneficial and increases the collaboration across the program management community. Again, I already mentioned the cost community, the test community, across the broad set of acquisition community stakeholders. Now, when I talk to you about models, Jeff distinguished, and I agree with his articulation, that there really is a fundamental difference between modeling and simulation. But when we talk about the modeling, there's a wide range of artifacts that we're really talking about, and the wide range of artifacts that we're trying to mature and integrate use of. And it includes not only the physics-based models that Jeff is talking about, but as well as data models, process models, and the algorithms that control many of our systems. The tools and processes that we are generating are not separate, but their integration collectively is what we believe can make a major change to the acquisition process, but really to enable that engineering function. And we believe that they are fully that they can be applied across the life cycle. So my office is trying to pull all this together through an initiative that we've kind of termed the digital system model, digital thread set of activities, where we have an opportunity to identify what are the data, what are the processes that are naturally used by engineers or needed by engineers in order to do those functions. How do we align that data that's being generated or used or required across the life cycle? How do we represent that data in terms that are normally in a taxonomy or in a framework that fits within the program management construct, that fits within the acquisition construct? And then how do we leverage ongoing initiatives that are generating this data? We're not in any way, this is really not about starting from green sheet or starting anew. This is really about leveraging and integrating the ongoing work and efforts, but doing so in a way that we're not diminishing anybody's capability to advance the state of this technology or this opportunity, but rather put in place a demand signal for the models and data capabilities that we seek to achieve. So in the end, what we're trying to do, as Ed described in the beginning, is develop a taxonomy that allows us to understand in a coherent fashion the technical data and the integration framework that we can use to integrate all the various modeling and tools and capabilities and to be able to exchange and collaborate when we're building digital representations of a system throughout the life cycle, to be able to allow us to communicate and collaborate cohesively across these multiple stakeholder communities. We know that there's challenges. We are on sort of the beginning of a journey. ERS, I think you're in your third year of, or so of a major program management activity, major community of interest. Owning the technical baseline and the digital thread, digital twin, really just emerging in the last year or two. And so we know that there's challenges out there, and we know that there's a lot of work to be done. I wanted to highlight a couple of those to you so that you as attendees of this community, at this conference, can be thoughtful about ways in which we can perhaps address these challenges over time. We right now do, as I mentioned, have many strong capabilities amongst our labs, within industry and within academia, where we're developing these tools and we're actually applying them in many cases. And I think the pilots that the Air Force has selected will really go a very long way towards expanding that capability and where it's being piloted. But we need to be able to continue that, to continue to expand that technology and share amongst it. So I think we need to, there's the challenge number one is to really leverage what people are doing and share it in a fashion that it can be used throughout the department. We need to really establish a demand signal. We can have the best engineering design teams, but if there's not a demand for that strong rigor and that data, if we don't demand it on contracts and the way that we do our business, if we don't institute it as part of our acquisition processes, this very, very strong technology opportunity will not come to fruition. And so from a policy and a process perspective, and really from a standardization perspective, we need to set that and define those engineering processes that will more repeatably rely upon models as part of its foundation. We also need to make sure that we don't oversell. So, already the term digital thread and system model have become really like a buzzword, and the department sometimes gets behind a buzzword, and then it loses meaning. And so I think one key challenge is to like the gentleman did here today, define what we're talking about very specifically. And really don't oversell the technology, but really take best advantage of it. I lived through simulation-based acquisition days. So about 10, 15 years ago, the department was going to change everything and take advantage of simulation. And we were going to do SBA. And I think at the end, we oversold and we got lost in the buzzword. And we definitely advanced the simulation capability in the Department of Defense. But in the end, I don't think we achieved the impact and the effect that we wanted to have. I think today we have a different opportunity because I think the technology's actually advanced to a much more mature state. There's real opportunities to apply it, but a big challenge will be to make sure that we do this in a discrete and purposeful fashion. And then the integration is the biggest challenge. I think Jeff talked about it. When we have multiple types of models across multiple types of stakeholders, the ability to integrate across those different models and the communities that have developed those models is really a technology challenge, and that's one thing. That's why the ERS initiative is so critically important, and it is one of the priorities of the DoD research and engineering investment and strategy. And so in the end, I think just to summarize what we've all tried to explain to you here today and share with you as part of what this initiative is about is in the end, we hope that we'll be able to actually transform the state of engineering and improve our workforce capability. Here I say organic. I think it's not just organic. I think that's a very DoD centric. Of course, I care about my workforce, but I think we can improve the nation's engineering capability and enable our workforce to really improve. I think we're going to have an ability to create an enhanced communication inside and outside from the Department of Defense. I think we're going to have an ability to have process efficiency. I think we're going to be able to, and what I mean by that is that I think today we do a lot of studies and analysis, and we come to a decision point, and then we go to a next phase, or we award another contract, or we move on to the next part of the program, and we throw all that analysis away. I think what we're going to see is a real impressive opportunity to grow knowledge over time, to better understand that system representation over time, and not repeat the analysis, and not wonder why did we make that decision or not repeat those things over time. And then I think fundamentally also we're going to be able to have better informed decisions near term as well as far term. So that concludes my remarks. I think we're going to have some time for questions.
So we have plenty of time for questions, and we have a microphone in the middle floor, so don't be bashful. Like I say, you have the Department of Defense experts and process owners in front of you here, so I'm surprised, really, Paul.
Well, this is, to use a previous DoD buzzword, this could be really transformational. No, this is a great initiative. People have been thinking about this for some time. Both Kristen Baldwin and Dave Walker talked about SIM-based acquisitions, SIMAF, all that from 15 or so years ago. There were, I think, a couple issues that happened then that I hope don't happen this time. It's thought about. One was we really had an idea back in SIMAF days, in the early days, to kind of have the as-built models, at least at the block level, maybe not at the tail number level. But we never were able to really keep the models current and up to date. And so that's going to require, policy and execution to really keep them up to date. And I think that is important. And as you each have pointed out, the capabilities we have now are much better to be able to do that. We have more storage, we have more computational cycles, all that. So I think that's something very important. The other thing would be who's going to own the models? In the past, we never quite made the leap to having the government really own the models all the time. And I think the government has to own the models. And I think it's really important then to have the workforce that has the capability to understand the models, how to use them, and also the assumptions that went into them. Because sometimes after models have a long life, nobody's there that really understands what went into the models, and they get applied in areas where they don't have as much relevance. So I think those are things that have to be addressed to make this successful. I know you're all thinking about those, and I just want to give you as much encouragement and support as I can, because I think this is a really important initiative and kind of reflects the advances of technology that we've had in the last 15 years. So are there any comments you might have on that, what you all are thinking and how you look at that?
Yeah, I'd actually like to address the workforce issue on there. One thing that we've allowed to happen over the last 20 years is through acquisition reform back in the 90s and our lightning bolts we did in the Air Force, is we allowed our engineering competency to atrophy. And we don't have the engineering expertise right now to be able to do this. And so Ed mentioned earlier about the engineering enterprise that we have in the Air Force and our revitalization process we have ongoing. And that's a big part of that is, we're looking at about a 10-year process to try to rebuild that engineering competency. In the meantime, we're going to have to still depend upon prime contractors as well as AIAA contract support to be able to go out and buy expertise where we don't have it. But we've got to start building it back again or we'll never get it back. So it'll be an ongoing process to do that. SBA actually had some good, there were some really good aspects of it. know, people don't realize that we tested out the JSF in the red flag environment with a live virtual blend. Actually, it was a live virtual constructive blend that we did, and learned a lot from that. The problem is that was in '99, and here we are in '14, and we didn't learn the lessons and continue moving it on. One of the problems that we have is that the way we fund acquisition programs is not conducive to having a long-term model-based process, because each acquisition program is responsible for their own models, and in each phase is responsible for their own models, as Kristen said, and we allow that to, you know, when you start a new program, you start a new phase, you start new sets of models, and you rebuy the models. Nobody's maintaining the models. We don't have the policy that says, we're going to maintain system models as a government-owned or government-controlled system model that we have oversight and purview on. And we need to do that.
The CREATE program for on the physics-based side,
Yep.
kind of developing, I mean, really high-end tools that the whole community can use, that can be maintained and added to with time.
Yeah, I might amplify a little bit of that and a direct answer to some of your questions, because we have thought a lot about that. Who's going to own models? How do you manage models? How do you sustain? Because you're going to be looking at 30, 40-year life cycles of systems.
100 years.
100 years. And what's important in the context of the digital thread we're talking about, and it's generated by CREATE type tools, is now I can take really high fidelity, multi-physics, multi-domain simulations of a vehicle, and we don't carry all the gazillion zeros and ones from CFD solutions around. We immediately transfer that into what we call an authoritative digital surrogate. And the simplest way to think about it is a reduced order response surface. So given an outer mold line for a concept vehicle, within days to weeks, using tens of thousands of processors and the tools that have come out of ERS, we can generate that response surface. Now the value of that thing is I can take that response surface, I can go into war games, engagement models, and I can look at mission utility. I can look at using set-based design principles. I can look at every design variable you can think of, and I can chase that through every mission scenario set of parameters you can think of, and I can find the sweet spot. Now it gets even more exciting with that digital surrogate representation, that fly-out response model. I can pick that same thing up and go right into the SIMAF facility with it. That's the driving engine inside the SIMAF facility. Now I'm into a live virtual constructive environment. I'm a node in a distributed mission operation. And we're talking with folks at SIMAF. Now, if you start looking at open architectures and avionics test beds, I can be looking at interoperability for a concept vehicle. And I can be looking at networking. So that's a shift. Now, that same surrogate response service, that same flyout model, now lives over the entire life cycle, because that just came out of developmental planning. Why would I throw that away? I pull that in through the detailed design process the OEM is going through, and what he does is enriching that response service, the flyout model. I'm in a test environment. As soon as you tell me there's a flyout response surface available to me, I can build a temp around that response surface. I can find an optimum test campaign to reduce cycle time and cost, ground test and flight test. I can do that pre-milestone A. I don't have to wait post-milestone B and then just do things on the fly. So I can revamp how I even do business. The same flyout model, if you think about it, goes right into trainers as you go downstream. And so that's the context of the digital thread. You have a single authoritative representation of the system any point in time, and the enterprise owns it. Now, the challenge there is there will be times that we need to be proprietary information for obvious competitive reasons. But it's different than having to know the detailed proprietary ways that an OEM does business, because all I'm getting is that surrogate representation. I don't have to have the secret sauce, I just have to have the surrogate representation. So we have been thinking about that, and sustaining that authoritative representation is a whole lot easier than trying to keep up with 50 different physics-based models and on all their detailed 0 and 1 outputs. That's not what we're talking about here. Now what you want to do is make sure you have the mature subject matter experts and tools in each of the disparate domains that can generate that information, put it into the digital thread, and then sustain it over the life cycle. So I think that simplifies, a lot of the problems we had earlier. So.
One of the other things that we're finding out in SIMAF, SIMAF's a great tool, but SimAF has tended to be very much a point solution type approach. And the ISR community really wanted to look at how do I make decisions across multiple domains, across multiple systems. And to do that, there was no tool available to them. So that's where this multi-resolution analysis process came into place, that they've helped SimAF develop that domain for ISR. Now we want to extend that under the air dominance initiative. How do we move that into the air dominance domain? So we're trying to see if we can continue to build SimAF to make it a much greater tool for the Air Force so that we can do analysis across all the mission sets that we have in the Air Force and be able to use that as our non-advocate tool to be able to analyze different concepts coming from different contractors and make decisions for the future that way.
One last thought on this. You know, there are some strong pluses of where we are today that would not have been true even in the year 2000. All right, so we know a number of things about how to model that we simply did not know how to do. We thought we did. The CFD community, for example, would have been by far and away the most advanced of all the communities in the year 2000. There are still a number of things at the university level where we were saying that we could model store separation when in fact whether we could or not was still problematic at that point. Last 14 years has seen a major change, and especially in the last 6 years, in what we're doing. Create is a result as much as a cause of those types of things. Second thing is that we have a number of the kids that we get to recruit today have a lot better computational training, I believe, at fundamental levels than they had certainly when I was going to school, when the abacus was the closest thing to, and I don't mean the structural model abacus is the closest thing to being able to do that. But here are our challenges. Every time we grow, we find other things that we simply do not know how to model. For example, we would like to be able to model cascading failure. And what we really need to be able to do is to be able to turn very high-end results and even surrogate results that we're talking about, reduced order models, into something that is understandable by a decision maker from the standpoint of risk buy down. And that requires that we carry uncertainty with us all along and that we get people used to understanding probabilistic answers, which is going to be a challenge in and of itself. So there's still plenty left to do.
Yes, sir.
Part of that atrophying DoD workforce. My question is, how do we implement this open architecture modeling environment? Can it be done at the working level, or does it need to come down as a requirement from?
I think the demand starts with at the OSD level, and I think actually in response to Dr. Nielsen's comment, that's going to be the driver for keeping the models up to date. I think without that kind of top-down demand, then the focus won't be on maintaining those models. But once that demand is set at the top, the architecture absolutely, I would say, has to extend down to at the lowest level, because we have to understand how the integration occurs, and it occurs at the lowest level.
Another aspect, having the top-down policy absolutely will drive this, but the more critical thing and part of the value of having this kind of fidelity very early, pre-milestone A, in the sense that I can write a systems engineering master plan and a test and evaluation master plan that early. When I go into the pre-milestone B RFP phase, putting language consistent with what we already know about how the system could perform and how we're going to evaluate it as the government into RFP language, that's going to drive a whole different mid-level engineering level approach to how we do business. So that's the critical thing, the top-down policy and then injecting appropriate guidance in RFP language to make sure we get what we're asking for.
Much like we've learned with the open system architectures for avionics, is that if you don't define the standards, then everybody's open, it's just that they're not open to anybody else. Mm-hmm. And so we're finding that the same thing as we look at models. We're starting to drive from the SimAF, the Eagle simulation language as being the key for operating within SimAF. You need to bring your model in that language to be able to operate and be interoperable. The Create AV brings an opportunity to where we have a environment that you can operate in that is interchangeable amongst other models. So we really have to start putting in our requirements is that these are the deliverables, and deliverables will be given to government standards and not to whatever a particular proposal wants to have. And we haven't done that in the past, and that is one thing that is incumbent upon the government to start doing.
Yes, ma'am.
Debbie Zakar. I work for the Naval Research Laboratory, and I think we've already started doing some of this amount of work, at least amount of paperwork. And so some of the documents we write are like 300 pages, and we get the same question over and over again. So is there advice that you guys have to help clarify our documents so that maybe they're the same across our programs so that it's easier to find the data and correlate it all together?
Documentation. So from a documentation perspective, are you talking about documents like the systems engineering plans and requirements documents?
Well, I do thermal engineering, so it was like our model description. And also, you know, at the end, they will have like a end item data package with all these papers all together.
I think that's more of the process we're in right now. You know, the vision for this is like on the order of 2 years old, particularly the Air Force's digital threat approach. And we're in the process using the OSD level taxonomy of what are the decisions that have to be made in the entire life cycle. What engineering parameters do you need to bring to that decision space? What probabilistics do you have to identify uncertainty? And then you start cascading down. Now, how am I going to generate that? And then that will lead into the taxonomy and the family of digital representations that you'll evolve and maintain over the system. So that's a work in progress. So maybe that kind of documentation of what am I going to use, when am I going to use it, how am I going to use it, that's, the pieces are out there. We're now learning to organize that. And really we need to weave that thread that we're talking about. But the end game here is not models. The end game here is support to risk management and decision making. And so that's what we're looking at, is each of the critical decisions over the life cycle. What do you mean by that decision? And what is it I really have to, from the engineering community, bring to the table? So that's where we're at in the process.
The owning the technical baseline, the 4 pilots I talked about with the J-STARS and TX, the long-range standoff, and the OCX, those are the kind of questions we're trying to answer, because we really don't have the answers to them yet. And so we're using those pilots to try to help us understand what is it that we need to have, how do we write the proposal or the RFP so that we get the right information, and what's the balance between what does the government have to own and control versus what does the government have to have access to? I don't have a good answer yet on those.
One thing that could be helpful to you, though, is that if you're doing stuff the first time, it always looks remarkably hateful, all right? So what we need to be able to help you with is how we create a set of processes that allow you to reuse as much as you possibly can. So for example, instead of creating hundreds of Word documents, not that you are, but instead of doing that, perhaps what we need to do is to capture all this stuff in SysML documents where you simply change attributes along the way, and we follow systems engineering constructs that way. And those are things that we'll work out. But I would say you're honestly probably 5 years ahead of where we're ready to be to give you a definitive answer for that.
Yes, sir.
You talk a lot in the words that we're here about and innovation as well, and failure was never part of that. And if you're really pushing the envelope, most of your experiments should fail. And the culture, certainly, what comes in the lab is that failures are very, very bad. It forces us to be conservative. What are you doing about getting a culture where failure is the expected value? They expect you to fly the wings, expect you to push the envelope and find out unknown.
Yeah, it's a challenge in terms of changing the entire culture of the U.S. aerospace industry. But a big part of this and the value of the constructs and the tool sets we're talking about is do a lot of virtual experimentation. So I think we can cut down a lot of risk and find things that don't work, overtly don't work through that process, and try to minimize the ones we'll find experimentally. And then it's the rapid prototyping, it's the early experimentation, it's the prototypes. So I don't go rocking along 7, 8, 10 years and then go into the flight readiness reviews and first flight for the first real piece of hardware. I figured that out with a lot smaller expenditures of prototypes, and I go ahead and take that risk. I think that's what's going to drive a different risk behavior. Dave, you see it that way?
Well, from the lab perspective, you ought to have more failures. I think that's one of the things that we don't emphasize enough in the Air Force Research Lab. I know in the past that we pushed hard that we ought to accept that, but then we don't incentivize it through our measurement systems and metrics that we have in place. One of the things that the reason we're doing the prototyping and experimentation initiative is that when you go beyond the lab right now in the Air Force, the only thing beyond the lab is the acquisitions. Well, once you go into acquisition, failure is not acceptable. And in fact, you're supposed to have proven technologies, TRL 6 or beyond, before you go into acquisition. And so we really don't have a way of testing out ideas and playing with concepts and playing with technology, both virtually and physically, and finding out what works and doesn't work, and changing warfighting based upon new technologies being injected into the systems. So that's what we're trying to do with that initiative, is how do I give the opportunity to go out and try ideas without having to have a program of record already established that now failure is a major problem. None McCurdy have to justify to Congress why I did what I did. That's part of what we're trying to do there, to allow more of the risk-taking approach to acquisition in the future, so that I don't want to have risky acquisition programs, but I want to take risk before I get into them.
I think from an acquisition perspective, the culture that we're trying to change is to not be risk averse or try to avoid risk, but rather encourage the identification of where the risks are and have plans in place and facilitate better management of those risks. You'll see that in some of the better buying power initiatives and some of the new ways that we've actually modified the acquisition process, where we still have major gates, but we're really trying to focus resources and program plans on technical risk reduction activities and embracing prototyping opportunities and concept design and development opportunities to really highlight and use the identification of risk to drive our decisions to go forward.
So if you take those threads and you tie them together, what you would like to do is identify risk as far to the left in acquisition, in the global acquisition process, as you can, because you increase the cost of incurring risk at least an order of magnitude for every step you take as you go to the right. The key to doing that is to first understand, that you have risk and to accept it, but secondly, to actually identify where those risks really are. And what we've done in many of our acquisition programs is we've identified risk and misplaced what the real cause of the risk is, in which case we can't deal with it except through billion-dollar fixes later on.
Yes, sir.
Hi, I'm John Karsten, TSTI. Thank the panel very much. Interesting discussion. We've faced this many times in the past, different companies I've been with. My question is based on contracts. Normally now contracts take over a year to get under contract. It's a problem, 14 months, 18 months. D3I, the proposal was put out last spring, 2 years to evaluate that. What do you plan on doing when you talk about buying power and doing that? How will you enable the industry and contractors to get under contract faster, and what are those mechanisms that you plan on doing? And again, to reiterate kind of what Paul was saying, with the authoritative model you're talking about, would you imagine using seadrills to capture that type of data? How does the government go out there and really grab a hold of that?
I think yes. So to take the last part of your question first, what we're trying to do as we develop this framework is to, and the reason why we're trying to utilize existing management structures or work breakdown structures as a taxonomy, and use the existing acquisition process that drives engineering artifacts and data as the basis, is so that we can actually easily, hopefully, modify and develop new seed rules that augment the contracting process to request data in new formats, just as an example. You know, with respect to the first part of your question, I'm not a procurement official, so I can't really talk about what we're, you know, specifically doing to the contracting process. But you know, we do need to be able to engage with industry much earlier in the process and have a mechanism by which we can exchange and share and develop these concepts. So from an engineering standpoint, we see the incredible value, and we need to be able to have the contractual mechanisms to allow us to operate. This is once again, as I mentioned before, I did have the word organic, you know, and I'm very biased towards wanting to build my workforce, but we really absolutely have to work this in a very collaborative fashion with the industrial-based workforce and the government workforce, and so those contractual mechanisms are fundamental.
I need to point out too, this even though this is being driven by the Department of Defense and the services, this is not being done in a vacuum. You know, we've been very active interacting with industry. There's a digital thread working group focused at Wright-Patterson Air Force Base, and they meet very high frequency. I'm talking multiple times a month, and they talk through these kinds of issues. And you know, the definitions you saw Dr. Walker put on the table, that was formed in conjunction with industry. So we are playing with industry. The other thing is the CREATE program, the CREATE AV program in particular. The last 2 years, they've funded, they've had broad area announcements and funded industry to come take the tools, take them back in-house and use them the way they would in their own processes. Well, the only expectation is tell us what works and doesn't work and how would you use that. So industry is already engaged in this. This isn't like we're gonna do all this and go write it down and then throw it over the fence to industry. Industry is helping us design what this will look like in the future. Yes, ma'am.
Before you move on, one other point on that. Part of the 4 pilots is really trying to understand what are the contracting changes we need to have. How do we change our RFPs? How do we change our seed rules to provide us the information that we need to be able to have the digital thread, as well as to provide the information to the contractor as to what their role is in this. And so the long-range standoff missile is one that I've been working very close with on. They realized very early that they can't do what they want to do in that program under the existing approach that we have to getting information on the reliability and the manufacturability of the missile the way we have done it in the past. They know they need to change, they just don't know how yet. And so that's a lot of the pilot is trying to really understand that, and a lot of work they're doing with the DOE and NRO and other agencies that work reliability to try to understand how do we change our contracting process, and then working through the Air Force and the OSD contracting community to start developing the new seed rules that are required there, and to really put that in as part of our standard contracting process.
Yes, ma'am.
Thank you. Vicki Johnson from the Development Assurance Team at Textron Aviation. I come from the civil aircraft world, and there's been a lot of discussion about risk and the desire to give managers the ability to better identify and mitigate technical risk. And I'm wondering if there's any work going on or any look in the civil world. We look at, for technical risk, the level of failure, what's going to happen, is it catastrophic or hazardous, major, minor, no system effect. And depending on that, we actually modify what we do in terms of validation, the number of validation methods used, the level of independence of the people doing those methods, and then when you get to the design implementation verification, how many levels you need to do and the level. And I just wonder, it's been kind of ongoing in civil aviation. There's a big push now to do more of it. do it more rigorously from the top to the bottom, from the airplane all the way down. I'm wondering if there's any look at that or any applicability of that in the acquisition world.
We use a very similar process in actually managing risk. The biggest issue that we have is identifying risk. And that's where we're really trying to use the digital system model and the ERS approach to be able to identify risk earlier, and then from there to develop mitigation processes, which follow a very similar type process that you described there.
You know, part of that is in the development of digital thread and application of a physics-based model. We're trying to borrow something the Department of Energy does very well, and that's quantified margins and uncertainties. So one of the values of doing set-based design and have all the probabilistics and not looking at deterministic single-point designs is you now have sensitivity to design variations. So at each stage where I'm making decisions, you know, at a PDR, a CDR, a flight readiness review, or low rate production or full rate production, and this bubbles up, for example, at Dr. Walker's office, is, okay, I've come this far, we've designed this system as an enterprise, and I had a KPP for a certain range, and I'm only getting 80% of that range. What's my risk of accepting that or not accepting that? Well, that tool set we just developed, that digital thread, tells you pretty much what's the mission utility you lost because you only have 80% of your range. Can you live with that? Or the inverse question is, I can't live with 80% of that KPP. I have to have the full 100%. Now what's it going to cost me to get that 100%? Can I afford that as a nation? So that's the other dimension of the risk, and having that digital thread construct really reinforces and enables that kind of decision making. So when it comes up, as I said to Dr. Walker, and he has to certify to SAF-AQ and then on up to Mr. Kendall, that now we've looked at this and we got quantified information that says it's your trade space. You know, you can live with it, or you can kill a program, or you can pay the price to get the mission utility you have to have. And so that's the other dimension of risk we see.
Yeah, I don't think in any way is this just to satisfy management decision-making requirements. These are engineering and technical and testing. So I think we don't want to. I think we want to celebrate what you're doing, and I do think it's very similar. I think, you know, Jeff would say the same thing. The types of decisions that we're trying to prove at a very deep technical level through the physics-based modeling. You know, that what we're trying to do is maybe try to see if we can connect that to a decision maker, but we need to continue to grow and mature that capability for the very technical community. We're not just trying to do this for management only.
Yes, sir.
Hi, my name is Ed. I work in your aerospace FRL. One thing I've been a little disappointed about, we've talked about all this. Nobody's talked about the acquisitions. 30 years isn't going to cut it. How is what this is doing going to help that? That was one point that I saw. But the major thing, the last decade of my life has been in modeling level. We can't model everything. We don't know what to model. 2 examples, the O2 system. We could model it. We didn't know how high we needed to model it. Space shuttle. Nobody thought about modeling foam strength. How do we handle these unknown unknowns? Risk. A lot of the things that we should be doing in ARL, from my perspective, and I'm a young guy and I apologize for that, 35, I am the youngest guy in our branch, but I probably the youngest guy in the room. Yeah. So I agree we have a huge problem on the workforce. I think that's been covered. But a lot of that work that we should be able to try to work in parallel with industry and apply the methods we develop in AFRL with these programs. Going to DARPA. I work in the future air dominance application area. AFRL isn't getting that work. My perspective, we should.
let me take on the first part of that, cycle time, and if you got about 3 hours, I'll give you a real detailed briefing on cycle time.
He will. No, he will.
I could answer. Thank you.
Because that is a driver. You know, the second pilot Dr. Walker talked about, and here's real data. You know, the F-22 took 174 months to go from milestone B to IOC. The F-35 is 210 months and counting. That's cycle time, and that's at about an $8 billion a year burn rate. That's huge. Okay, so that's the target of opportunity. Now, what we're specifically looking at is development, test, and evaluation. Again, when you look at how does that fit in the scheme of acquisition, it overlays 85% of that cycle time. So if I can take a 4-year wind tunnel campaign and cut a year out of it with this process, that's a big deal. If I can take 2 years out of the flight test campaign, that's a bigger deal. So that is right on the forefront of what we're looking at. That pilot, looking at developmental test and evaluation, is specifically looking at how can I reduce that cycle time. And that's really the attributes of the digital thread. It isn't just that we can do what we've always done with just slicker tools and nice things. It's, can we really change the paradigm? Can I take 200 plus months for cycle time from milestone B to IOC, take it back down to 100 months? That's where we have to go as a nation. So we are definitely doing that. Now, you know, will there always be unknown unknowns? Absolutely. You know, could we have second guessed the oxygen problem on the F-22? Probably not. But I see the same tool set is really addressing things like airframe structure integration. You know, I've got a data set that tells me we have probability 1 that you'll find 10 structural failures after first flight. Well, in the future, I like that not to be a probability of 1. I like to be a lot smaller than that. I also know that after a first flight, you're going to redesign the inlet because the engine and the inlet don't quite really work the way you thought they would. So how can we use these tool sets and these thought processes and move that integration problem much further upstream? So I think, you know, we are paying attention now. Are we ready to get all the way down to an oxygen system in the system? Unless we realize that's a perennial problem, we probably wouldn't. That would be a surprise to us. But I think we're attacking the bigger problems. How do you do the major system integration, the airframe structure interactions, the airframe propulsion interactions, the airframe weapon interaction? Do I design an aircraft to actually deliver weapons, or do I add weapons to it later on? So those things are being addressed with these models. Yes, sir.
My name's Ed. I'm in the same branch from Ed. I'm probably the oldest guy in the branch, 52. And I'm also part of the digital twin team with Eric Twiggle and Pam Coburn. I've been very impressed with what I've seen with the physics-based modeling concerning rigid CFD at that highest fidelity level. My question is, when you look at the number of analysis points you need to do, are you planning on filling out the full envelope, also covering the structural dynamics that are going to be associated with that at that high of a fidelity, where you're going to try and do mesh deformation and things that we know are very problematic for the Navier-Stokes solvers?
Yeah, I can take it down, and I see Bob Meakin walked in. Bob Meakin is the program manager for the Create AV program, and for fixed-wing aircraft, one of the phenomenal things they've done is they can do a very high fidelity representation of a platform given the outer mold lines. And the mindset of the CFD community is they're trying to replicate what a wind tunnel does, and that's dumb. Okay, if I do a CFD calculation at every angle of attack, every side slip angle, every Mach number, every altitude I simulate in a wind tunnel, which is 2.5 billion data points for stability and control, you got about 100 years to wait. Okay. What they have innovated, and it's really phenomenal, the way their architecture is, they can take that high fidelity model, and for a single Mach number altitude, in less than 2 days, they can put it through what's called a chirping maneuver. It's a sinusoidal variation, alpha and beta, and they can go over the entire regressor space. Then you use the same process you would use in flight. If I'm flying a trajectory in flight, I use system identification, I extract aerodynamic coefficients. So changing frequency and amplitude, and I get, in less than 2 days, I get a complete definition of performance and stability control. And oh, by the way, a side product is actual structural loading, that one calculation. So yeah, we do intend to absolutely map, and that's using 3,000 processors. Give me 30,000 processors in 2 days, I got you 10 points in the sky. Give me 100,000 processors, and I've got your entire map in less than a week. So that is feasible now, and that's the advances the Create tools are bringing to the table. That is what has changed. The high performance computing assets, the kind of tool sets that Jeff and folks are really putting it on a table for
Yeah,
us.
I'm
So-
very
But then it's
impressed with.
taking that, and feeding that back into the structural models.
Exactly.
So that you get multidiscipline approach to design rather
Yep.
than just a aero design or a structural design.
Yep.
But that's the one thing that's lacking is the fluid structure interaction, and we know that some of those problems arise, when you start exciting the modes
Yep.
in the vehicle.
Yep.
No vehicle is rigid. So I guess there's that aspect we need to kind of try to be able to bring into the process there somewhere along the line.
Well, the architecture Create actually uses a Python wrapper and does a time marching. So at every step in time, they interrogate the aerodynamics and then deform the structure. So it is not. It doesn't have to be a rigid aircraft. No, by the way, you can move the control surfaces at the same time. So that's the kind of advances we're talking about, and they're here already. I think version 6 of Kestrel now has a fully integrated finite element analysis capability. So as you're doing the aerodynamic flow over the vehicle, you have all the information, and you can start the process evaluating structures. So that's.
I look forward to seeing that continue to grow.
Yep.
Speaking of Rick Tuggle from People Tech, I'm out of the Redstone Arsenal area. Speaking of looking forward, as a lot of the previous questions, how do we get from a level of effort from cultural shaping to actual teeth into our acquisition processes, the system engineering plan, milestone deliverables, beyond just procedurals that the contractors can really play around with, to develop that repository of models that are available? I deal with a lot of system of systems, family of systems stuff. And more often than not, you have a bureaucratic mess between individual program managers and services to put together a joint system of systems or family of systems, community of interest type effort. And so going forward, next 5-10 years, what do you see coming down the pipeline to actually put teeth into this process, to actually have models, and the models are actually available for use beyond just a program stovepipe?
You want to address that one, Dave?
Yeah, from my perspective, what we're looking for is really leveraging the, two things. One is I got now the Lifecycle Management Center, which looks over all Air Force acquisition, is being the responsible for setting the standards and maintaining the model repository, and then the CMAF being really the owners of that within the Lifecycle Management Center. In the past, we haven't put any standards upon programs, so every program does whatever they want to, including if they want if they want a model, they build their model whether it exists or not. We don't have processes in place yet. That is something that we need to put in place to be able to try to get control over the proliferation of models.
We established a modeling and simulation catalog, and it's just, it's now being integrated into the DTIC, Defense Technology Information Center, correct? Right. So DTIC is launching the M&S catalog, and it is the goal of that catalog to be a central repository that won't necessarily contain the models in that catalog, but will contain enough of metadata about the models and pointers to the different types and where to get access to the expertise and the model itself. So that's one initiative. And so I would say in the next 2 to 3 years, I would really like to see that catalog be populated and become this force to enable the type of activity that you're talking about.
It shouldn't be lost on you that we have Kristen here representing OSD Systems Engineering writing Department of Defense policy on acquisition. And then Dr. Walker is Chief Engineer in the Air Force, giving guidance all the way down to the PEO structure to the program managers. That's different than engineers bottoms up trying to talk to a program manager. So recognize you've got the two people at the top of the pyramid that are going to be driving these process changes.
So you've still got the bottom and top thing we talked about before, both of which have to happen for transformation. You've got the policy from the top that says, let's do this. In order for that policy to be created, we have to have enough ground truth to believe that the policy that we're promulgating is actually going to make something better, as opposed to simply being a policy. At the bottom level, one of the things we have to do is we have to consolidate the number of tools we have. We do not need hundreds of Navier-Stokes solvers. We need 10, pick a number, 10 really good ones that represent 90% of all of our utilization. And then we invest in those corporately. We hook stuff to them and we build them so that they can follow the business processes that we've created. That's basically what Create has done. The genius of Create is not just the computational prowess, but it's the fact that it fits into a business process. And those two things together over time will cause what you were describing to happen.
Hi, I'm Richard Mutzman from Air Force Research Labs, and I got a kind of a different type of question to ask you, since we have some of the thought leaders and most of you are all systems engineers, as I am. The question is, you know, the acquisition process is really a system of systems. What we've been discussing today is kind of the engineering process, or part of the engineering process. Somebody brought up issues with the contracting side when it comes to acquisition and the timelines and the costs associated with acquisition. The financial system, financial processes. Has anybody within the OSD or at that high level taken a look at maybe applying some of our systems engineering processes to try to analyze the acquisition process as a system of systems in terms of modeling, so that as you start proclamating new policy, we can see what effect that has on the overall acquisition process. You're talking about creating policy for new seadrills. What's that going to do to the contracting side of this whole thing? What's it going to do to the financial aspects of the acquisition process? I just don't, I've worked in acquisition, I've worked at Aeronautical Systems Center before coming to AFRL, and I never see anybody trying to attack this as a holistic system-to-system problem. Everybody works in their particular niche, but nobody looks at it from a broader perspective.
If I may, I think the development planning initiative that the department took on, really historically, grown by the Air Force, but that initiative is where we actually did what you're saying. We didn't just craft. We were driven by legislation in 2009 that the Department of Defense will instantiate development planning. Well, we didn't just write a policy and say, here's, okay, we've done it. We modeled, we defined development planning. We modeled the early pre-milestone MDD, which is the material development decision. We did a business process engineering model of all of the stakeholders that engage in the acquisition process, and we modeled pre-MDD, MDD to milestone A to milestone B, and we actually used that model to define the and pilot. We pilot it first. So I think, as I reflect on your question, we absolutely did employ good systems engineering practice to understand the environment, understand the implications, understand the needs for where we had gaps in policy. We understood what the baseline was and then how to improve against that baseline. And that's what drove what is now being codified in the latest version of the 5000 that redefined what a material development decision is, what are the data and criteria that go into making that decision, what happens in that next phase, and so on and so forth. That was all. You don't see that as much outside of, I think the policy shops, but we don't just, much as people like to say, we don't just write policy, or actually I'll just say, systems engineering doesn't just write policy without understanding it, testing it, and really trying to validate it.
From an Air Force perspective, this is not an engineering push, this is an acquisition push. This is coming from Dr. LaPlante. The reason I talk about the seed rules is because to be able to implement this, you've got to change how you do contracting. You've got to change how you do program management. You have to change the philosophy of acquisition. So yeah, you're correct. You can't do this as just, we're going to go do this in engineering and we'll continue doing everything the same way we always had the rest of acquisition. This is across the board in acquisition, a change of philosophy of how we do it.
You know, Dr. Walker in the 3 pilots, he talked about one of his requirements for the 3 teams doing the pilots is they have to come back not with just the technical validation they can do it and the tool sets work and all that good stuff, but a business case to go with it. And the one I'm working in terms of reducing cycle time for developmental wind tunnel campaign, I can give them the short answer. Boy, if I can take a year off a wind tunnel campaign, I can name the hours I'll save you in the wind tunnel, and it's X millions of dollars. Okay. But the real discussion you want to have is, what am I doing to the systems engineering process if I take a year off the wind tunnel campaign? You know, and where are the long poles in the tent at that time? And if you look at the cost distribution in an acquisition program, the max cost of the program are right before first flight. And that's right where the wind tunnel campaign sits. So I may have a profound impact if I indeed, no kidding, can get that year out of the program cycle time. That could be measured in billions of dollars. So that's the kind of way we're going to have to look at the problem. It isn't a simple answer. I can save you, a couple thousand hours of wind tunnel time. No, it's, can I take the cycle time out of the acquisition process, because I've also interacted with all the other systems engineering things that are going on at that time. So and as Kristen pointed out, they did a SysMill type modeling of the entire process and find out where the leverage points are. But as we prove out these tools work and we attack particular parts of the process, we have to come back with that business case and also, I think, a use case. Okay, now exactly how you do it, who's going to do this in order to make this an institutional approach to changing it. So.
Do we have time for another?
Yeah, we'll go a couple more minutes because we got a couple minutes start. Yes, sir.
I'm Ed Blosh from Lockheed Martin. The messages about the digital thread really resonate with me. The MRB stuff in particular, I remember at like you said, first flight, some things break. And they discovered, there's a problem. They couldn't connect when this part failed, well, which parts need to be looked at? And they had to connect people to each other and talking and which director and whose guy's responsible for what, and it was kind of a problem. So I know we put substantial discretionary effort into a product called CAT DM, which is DM is for data management, so that we could look at a 3D model of the F-35 and click on the part that broke and go back and find which loads was that part designed to. So if you haven't been briefed on that, you need to get briefed on that so that you at least know that there is a connection. That all happened before digital thread semantics was invented. But the demand signals are already there. They're being driven by, the need to do things faster, the need to meet the aggressive system development schedule.
Yeah, it's and appreciate your comments, and please invite me to come take that briefing, because it's something close couple we've been looking at is defect discovery, and can I start looking at these early engineering processes to avoid late defect discovery? So whatever information you can share with us, we'd love to find out about that. So, by the way, he also represents the Lockheed part that's been testing out Create AV tools, so he's got that hands-on experience.
Dr. Holland said, the top and the bottom pushing together.
Exactly right.
That was kind of a bottom effort that the structural analysis guys, and so I hope that we can connect that to the top effort.
See, I believe I know Dr. Walker's got to think about getting an airplane sometime soon, but let's give a round of applause to our panel here. I'll be around through tomorrow, and I think Kristen will be in and out tomorrow. And Jeff, you're here tomorrow? No, okay. But grab us in the hallway if you want to talk some more. And if you want to have your ears talked off, grab me and I'll talk your ears off about this. So but I appreciate everybody coming. This is a pretty exciting opportunity, I think.